paper titled Nonintuitive Optima for Dynamic Locomotion, the Acrollbot, explores locally optimal, efficient locomotion of a two-link planar robot mounted on a single, unactuated wheel. The underactuated system is particularly interesting as when linearized, it is not controllable, yet can still be stabilized about the upright configuration through simple control methods. Such a toy system is a good candidate for which to apply our optimization framework on, which results in at first seemingly unintuitive locomotion solutions. We aim to bridge the gap between non-intuitive, data-driven optimization and model-based methods for design and control of underactuated and dynamically stable locomotion. To help with visual understanding of the types of motions uncovered by the optimization framework, we start with a hand-picked system and find optimal trajectories for that particular system. Note the oscillations at link 2, the input to the system. This is perhaps suspiciously reminiscent of last year's Google DeepMind AI video on the emergence of locomotion behaviors for a full humanoid, where repeated arm punching into the air appeared to help stabilize and locomote the system. Another interesting aspect of the motion is that the center of mass leans backwards, away from the direction of motion. In comparison, the motions discovered with our optimization framework for a more traditional acrobot parameter type system, where both links are the same length and have the same mass, look very extreme and have a very high associated cost of transport. Our framework simultaneously optimizes both motion trajectories and robot design parameters. Shown here is the first discovered local optimum. The robot is made up of a tiny link 2, with all the mass of the system concentrated at that link. The rest of the system is almost massless. Note the oscillations, and that the system is very close to the upright configuration throughout the trajectory. The second discovered local optimum has a lower cost of transport, but is found less frequently by the framework. L1 in this case is not visible, and the mass distribution is the same as in the first locally optimal case. Since the wheel radius is much larger than the links, there is no longer really a stability issue. Since our optimizations typically result in system parameters with all of the mass located at M2 and a minimal length L2, we consider that perhaps a flywheel at the end of link 1 may be more optimal than a second link. From a controllability perspective, this also helps with system stabilization. Shown first is the resulting motion for a system with hand-picked parameters, followed by the optimal trajectories for a locally optimal system, which has a minimal length L1. Using ODE 45 in MATLAB, the below two movies are of simulations based on the oscillation principles used for stabilization and propulsion uncovered with our framework. In conclusion, our framework allows us to optimize both design parameters and motion trajectories simultaneously. It also works with completely randomized initial conditions, simplifying our search and allowing us to discover multiple local optima. By studying the simplified toy system, we have been successful in carefully analyzing and validating non-intuitive solutions, and discovered novel motion planning strategies that human designers would truly never have anticipated.